Massive neutrino pulses may have just changed what astronomers learn about our galaxy. Coming from Earth's galactic center direction, ghost-like particles could carry clues ordinary light cannot reveal. Such claim sounds impossible, since neutrinos barely interact with matter, yet detectors here can still catch faint signatures. Now comes the unsettling question. Was it really one burst, or something far stranger hiding inside cosmic noise? Stay close, because answers potentially reshape humanity's picture of Sagittarius A and its violent neighborhood. Subscribe so you don't miss this story. Then let's follow an invisible signal into darkness, where extraordinary discoveries might be waiting. That is where the real puzzle begins. A neutrino is one of the strangest particles in nature. It has almost no mass, carries no electric charge, and barely notices the matter around it. Billions of neutrinos can pass through your body every second without leaving a mark. Earth itself is almost transparent to them. That sounds like a weakness. It's actually their greatest advantage. Light can be blocked, dust can scatter it, gas can absorb it. A thick cloud near the center of the Milky Way can hide what sits behind it from ordinary telescopes. Neutrinos don't have that problem. They can move straight through places that light struggles to escape. That makes the galactic center especially interesting. At the heart of our galaxy sits Sagittarius A, a supermassive black hole surrounded by an extreme environment. Gas swirls through powerful magnetic fields. Particles can be pushed to enormous energies. Radiation fills the region. Violent events have happened there before, and scientists still don't have a complete picture of everything taking place. Now imagine trying to study that hidden region with something that can simply pass through it. That's the promise of neutrino astronomy. But there's a catch. Finding a neutrino is incredibly difficult. These particles almost never interact with ordinary matter, which means a detector has to be enormous, sensitive, and patient. Scientists don't watch a neutrino fly through space like a bright streak across a camera. Instead, they wait for the moment when one finally collides with something inside or near a detector and leaves behind a measurable trail. That trail becomes a clue. From its direction, energy, and timing, researchers can estimate what happened. One event might tell them very little. A group of events pointing toward the same region can become far more interesting. And this is where the word pulse changes the entire story. A random neutrino arriving from somewhere in the sky is expected. Even several unrelated events can sometimes appear close together by chance. A genuine burst, however, would suggest that something powerful released particles within a limited window of time. Scientists would then have to ask whether the pattern is real, whether the direction truly leads back toward the galactic center, and whether the apparent signal rises far enough above background noise to rule out coincidence. Those questions matter because a detection is not automatically a discovery. In science, the exciting part isn't simply seeing something unusual, it's proving that the unusual pattern survives every attempt to explain it away. So the invisible signal has given us a difficult problem. We may have particles that crossed enormous distances carrying information from one of the most extreme places in the Milky Way, but we still need to determine exactly what they are telling us. And if that connection holds, the next question becomes much bigger. What could be powerful enough to fire a concentrated stream of neutrinos from the darkest neighborhood in our galaxy? Sagittarius A enters the story, and suddenly that faint pattern has a much more interesting address. At the center of the Milky Way, roughly 26,000 light-years from Earth, sits a black hole with about 4 million times the Sun's mass. Nothing about that neighborhood is calm. Stars race around it, hot gas swirls through magnetic fields, and high-energy particles move through an environment far more violent than anything found near our planet. Yet here's the detail that matters most. A black hole doesn't need to swallow something to make the surrounding space interesting. Material falling toward Sagittarius A can heat up, magnetic fields can become tangled, and particles can gain enormous amounts of energy. Those particles can then crash into gas or radiation, creating showers of secondary particles. Under the right conditions, some of those reactions can produce neutrinos. That gives scientists a possible cosmic factory. But possible isn't proven. If a detector sees several neutrinos arriving from roughly the galactic center, researchers can't simply point at Sagittarius A and declare victory. The sky is full of background events. Some neutrinos are produced by cosmic rays striking Earth's atmosphere. Others can come from distant objects. A few can even land in a suspicious-looking pattern purely by chance. That's why the direction of an event matters. Imagine standing outside during a storm and hearing one clap of thunder. You might guess where it came from, but your estimate could be wrong. Hear many sharp cracks from the same direction at nearly the same time, and your confidence rises. Neutrino astronomy works with a similar idea, except the clues are far harder to collect. A detector doesn't see the neutrino itself. Instead, scientists study the particles created when that neutrino finally interacts with matter. Their tracks can reveal an approximate arrival direction and an estimate of the neutrino's energy. Now the story becomes a numbers game. How many events appeared? How energetic were they? How tightly do their reconstructed directions point toward the galactic center? Did they arrive close enough together in time to suggest one event? Most importantly, how likely is it that background noise could create the same pattern? Those questions can turn an exciting headline into a serious scientific test, and that's exactly why this potential signal is so fascinating. The extraordinary part isn't simply that neutrinos may have been detected. Scientists have detected astrophysical neutrinos before. The real prize would be showing that a concentrated group carries a reliable fingerprint from the heart of our galaxy. If that evidence survives careful analysis, the galactic center could become more than a place we observe with light. It could become a source we listen to through particles. And now we reach the question that could change everything. What would a genuine burst actually look like? Because a handful of scattered neutrinos is interesting. A true pulse is something else entirely. And if the timing locks together, scientists may finally have the missing clue needed to separate coincidence from cosmic cause. And that distinction changes everything. A real neutrino pulse wouldn't simply be another dot on a scientific chart. If several high-energy neutrinos arrived within a time window and their paths pointed toward the galactic center, scientists would have a rare chance to study an energetic event through particles that can escape places light can't. That matters because Sagittarius A isn't an ordinary black hole. It's the supermassive object sitting at the center of our galaxy, millions of times heavier than the Sun. Around it lies a crowded region filled with stars, hot gas, magnetic fields, cosmic rays, and radiation. From Earth, much of that environment is difficult to study because material blocks our view. Neutrinos offer a different route. They can travel through dense matter with almost no interaction. A neutrino created near the galactic center could cross thousands of light years, pass through clouds of gas and dust, and eventually reach a detector on Earth. That sounds like a perfect cosmic messenger. Almost. The same property making neutrinos valuable also makes them incredibly hard to catch. Most simply pass through everything. Only a tiny fraction interacts strongly enough to leave a detectable signal. So imagine what it would mean if scientists suddenly saw a cluster. The first possibility would be that something had accelerated particles near the galactic center. Those particles could collide with surrounding matter or radiation, producing secondary particles that eventually generate neutrinos. In that scenario, the neutrinos would carry evidence of a particle accelerator operating somewhere in the most extreme region of our galaxy. But there's another possibility. The apparent pulse could be a statistical accident. Background neutrinos exist. Atmospheric particles exist. Detectors have limits. When researchers examine a small number of events, random patterns can sometimes look meaningful. That's why the strength of the signal matters just as much as the excitement surrounding it. Here's the detail that changes everything. Scientists don't only ask whether events point toward the galactic center. They ask how unlikely it would be for the same pattern to appear by chance. That calculation can separate an intriguing hint from a genuine discovery. If the evidence survives that test, Sagittarius A becomes one of the most compelling suspects. Still, we shouldn't jump straight to the black hole itself. Something else in that crowded region could be producing the particles. A supernova, remnant, dense gas cloud, energetic stellar system, or another accelerator could potentially create high-energy neutrinos. The galactic center contains enough extreme objects to make the detective work surprisingly difficult. That's what makes this potential signal so valuable. It isn't merely asking whether neutrinos exist there. It's asking whether we can use them to identify hidden engines of cosmic power. The invisible could become a map. And there's an even deeper question waiting behind that map. If these neutrinos really came from the galactic center, what happened there when they were created? Those particles may have started their journey thousands of years before humans ever knew they existed. That delay creates another strange problem. When a neutrino reaches Earth, scientists aren't seeing the event as it happens now. They're seeing an ancient message that has traveled across the galaxy for thousands of years. But how can anyone know where that message came from? The answer begins inside the detector. When a neutrino finally interacts with matter, it can create another particle that leaves a visible trail. Scientists measure that trail, calculate its direction, estimate its energy, and then work backward toward the patch of sky where the neutrino probably came from. Probably. That word matters. Unlike a flashlight beam, a neutrino doesn't arrive with a perfect arrow attached to it. The reconstructed direction has an uncertainty. Sometimes that uncertainty can cover a large area of sky. If the suspected source sits near the edge of that area, the connection becomes much harder to prove. Now add the background. Earth is constantly being bombarded by cosmic rays. When those particles smash into our atmosphere, they create showers containing particles that can imitate some of the signals researchers are searching for. The detector has to separate the rare cosmic events from this constant stream of ordinary background. It's like trying to hear one whispered sentence inside a stadium. That's why scientists need more than one exciting event. They need patterns. Suppose several energetic neutrinos arrive close together in time. Their reconstructed directions overlap. Their energies are unusually high. Then researchers compare that cluster against what random background events should produce. If the pattern would be extremely unlikely by chance, confidence rises. If ordinary background could easily create it, the story changes. This is also where the word massive needs care. A massive neutrino pulse doesn't mean the neutrinos themselves are enormous. Neutrinos are incredibly light particles. The word describes the scale or intensity of the observed event, not the physical size of each particle. That distinction may sound small, but it's crucial. Science often turns on details that seem tiny in a headline. A signal can be real while its source remains uncertain. A cluster can be unusual without being statistically strong enough to call a discovery. Even a convincing direction can still leave several possible sources competing for attention. So the real challenge isn't simply detecting neutrinos, it's connecting the dots. Researchers need timing, energy, direction, statistics, and independent observations to line up. When those pieces agree, a faint particle becomes something much more powerful, evidence. And that's where the story moves beyond a strange signal. If the suspected pulse truly came from the Galactic Center, scientists wouldn't just have another detection, they'd have a new clue about how extreme particles are produced near the center of our galaxy. But one mystery would still remain: what engine created them? Because the black hole is only one suspect. And the next clue could come from something much more explosive, hidden deep inside that region. One possibility is a supernova remnant, and that possibility deserves serious attention. When a massive star reaches the end of its life, the explosion can leave behind an expanding shell filled with shocked gas and magnetic fields that can accelerate particles to extreme energies. If those particles crash into nearby material, neutrinos can emerge and travel away without being stopped. That makes a supernova remnant an interesting suspect. Yet there are other candidates. Dense clouds of gas near the galactic center could also act as targets. Imagine cosmic rays moving through space like invisible bullets. When they slam into thick clouds, particle collisions can produce showers of new particles, including neutrinos. The black hole doesn't even have to be the direct source at all. That distinction matters here. That detail matters because Sagittarius A is surrounded by a complicated neighborhood. Scientists must identify which object or process could explain the signal. Then comes an even stranger possibility. The neutrinos could be connected to an event that happened long ago, but the evidence only reached Earth now. Remember, the galactic center is about 26,000 light years away. Any particle arriving from there has spent roughly 26,000 light years crossing space. The actual event happened thousands of years ago. In other words, we're looking into the past. And that changes how we should think about a pulse. It doesn't have to mean something is exploding at the galactic center right now. It could be an ancient burst whose particles have only just completed their journey to Earth. Timing becomes especially important. If multiple neutrinos arrived within a narrow window, scientists could compare their arrival times and directions. A tight cluster would be much harder to explain than scattered events appearing months or years apart. But even a strong cluster wouldn't automatically reveal the source. That's where astronomy becomes a team sport. Telescopes observing X-rays, gamma rays, and radio waves can search the same region. If a neutrino signal appears alongside a change in another wavelength, the evidence becomes stronger. One detector can raise an eyebrow. Several independent instruments agreeing can change the conversation. And if nothing visible appears at all, that could be interesting too. Neutrinos might be showing scientists an energetic process hidden behind material that blocks ordinary light. This is the real promise of the discovery. Instead of asking only, what can we see? Scientists can ask, what can reach us? For decades, astronomy depended on electromagnetic light. Neutrino astronomy adds another messenger. Gravitational waves add another. Each one reveals parts of the universe that the others can miss. So the galactic center may be offering something bigger than one mysterious pulse. It may be offering a test of a different way to explore our galaxy. And there's one final problem left. Even if the signal is genuine, scientists still need to prove that it isn't coming from somewhere else. That is where the next piece of evidence becomes critical. What else has been passing through the galaxy unnoticed? A neutrino event doesn't arrive with a return address. Scientists have to reconstruct that address from the tiny traces left inside a detector, then compare the result with everything else happening across the same region of sky. The galactic center isn't empty space with one obvious object sitting in the middle. It's a crowded neighborhood. Stars, gas clouds, magnetic fields, cosmic rays, and energetic remnants are all packed into a relatively small region. Several of them could potentially produce high-energy particles. So, if a neutrino cluster appears to point there, scientists have to ask a tougher question. Does it point to Sagittarius A, or simply to the general neighborhood? That difference could change the entire interpretation. Picture a city at night. You hear a loud explosion somewhere downtown. Knowing the sound came from downtown is useful, but it doesn't tell you which building caused it. You need more clues. Astronomers face the same problem, except their city is 26,000 light years away. One way to narrow it down is through energy. Different cosmic processes can create particles with different energy ranges. If the detected neutrinos carry unusually high energies, some possible sources become less likely, while others become more interesting. Scientists can compare those measurements with models of particle acceleration around black holes, stellar remnants, and dense clouds. Timing provides another clue. A true burst should have some kind of temporal pattern. Events spread randomly across a long period are harder to connect to one sudden source. A concentrated arrival window would make the case more interesting, especially if independent observations show activity from the same region at roughly the same time. Then comes the hardest test of all, background probability. Researchers can calculate how often ordinary background events could accidentally create a cluster that looks similar. The smaller that chance becomes, the stronger the evidence gets. But even impressive statistics aren't the whole story. Every clue has to survive another question, another comparison, and another attempt to explain the same pattern independently. Scientists also want independent confirmation. If another neutrino observatory sees a compatible signal, confidence can rise. If a gamma-ray or X-ray telescope observes a related change from the same region, the pieces begin to fit together. None of those clues alone has to solve the mystery. Together, they can create a much stronger case. And this is why the word identified carries so much weight. Finding an unusual pattern is one thing, identifying its source is another. A headline can compress those two steps into a single sentence, but scientific discovery usually moves much more slowly. First comes detection, then analysis, then comparison, then attempts to disprove the explanation. That may sound less dramatic than a cosmic explosion, but it's actually more exciting. Because if this signal survives every test, it could give researchers something they've wanted for decades, a way to study the hidden particle engines operating near the heart of the Milky Way. And once that door opens, the next question becomes enormous. What else has been passing through the galaxy unnoticed? The answer could be hiding in the very particles scientists have only recently learned to use as cosmic messengers. For most of astronomy's history, space was studied through light. Visible light showed stars, radio waves revealed distant structures, X-rays exposed violent regions around black holes. Gamma rays revealed some of the universe's most energetic events. Neutrinos add something different. They can escape places where light may struggle to get out. A particle created deep inside a dense region can travel through material that would absorb or scatter ordinary radiation. Now, when that particle eventually reaches Earth, it can carry information about an environment that telescopes might never see clearly. That's why a galactic center signal matters beyond one possible pulse. It could help scientists build a different kind of map. Instead of mapping the Milky Way only by what shines, researchers could begin mapping it by what sends particles toward us. Think about that for a second. The galaxy may contain powerful particle accelerators that we haven't fully identified. Some could be connected to black holes. Others might involve stellar explosions, magnetic fields, or dense clouds. Their light can tell us part of the story, but neutrinos could reveal another layer. There's a catch, though. Neutrinos are so difficult to detect that building this map takes patience. A detector may wait for a long time before collecting enough useful events to establish a reliable pattern. Even then, scientists have to separate genuine cosmic signals from background noise. That means the future of this field depends on more than one exciting observation. It depends on accumulation. More detections can improve directional estimates. Larger datasets can make statistical tests stronger. Better instruments can increase sensitivity. Independent observatories can check whether the same strange pattern appears from another location. Each new event becomes another piece of the puzzle, and that creates an unusual kind of scientific suspense. The next important neutrino might not come from the galactic center at all. It could arrive from another hidden object, another distant explosion, or another region of our own galaxy. Any one of those detections could help scientists understand what produces the highest energy particles in space. That is the bigger prize. We're not simply trying to catch one invisible pulse. We're learning how to listen to a universe that doesn't always speak in light. Still, one question refuses to disappear. Was the suspected galactic center pattern truly a signal? Or did random events create something that only looked meaningful? That question can't be answered by excitement. It requires evidence. If future observations show the same direction, similar energies, and a convincing timing pattern, the case becomes much harder to dismiss. If independent measurements fail to reproduce it, scientists will have to reconsider the original interpretation. Either result matters. A confirmed source would open a new window into the Milky Way's most extreme environment. A false alarm would still teach researchers how sensitive their instruments are and where their models need improvement. But the next test could decide whether this story becomes a discovery or a mystery that fades into the background. And that test is already waiting in the data. That data could eventually decide whether this strange signal deserves to be remembered as a discovery. The first step is simple in theory. Collect more events. One unusual cluster can attract attention, but a stronger case needs repeated evidence. Scientists can compare future neutrino detections with the same region of sky and look for patterns that keep returning. If similar events continue pointing toward the galactic center, the probability of a random coincidence becomes harder to defend. Timing will matter too. A real transient source should leave some kind of footprint in time. If several high-energy neutrinos arrive within a narrow window, researchers can compare that timing with observations from other instruments. A matching flare in X-rays, gamma rays, or radio waves could provide another piece of evidence. Nothing has to work alone. That's the power of multi-messenger astronomy. Imagine several people describing the same distant storm from different windows. One sees lightning, another hears thunder, a third measures the wind. None has the complete picture, but their observations can reinforce one another. Astronomers are trying to do something similar with the universe. If a neutrino pulse is connected to a violent event near the galactic center, other observatories may eventually reveal what happened there. If no matching activity appears, scientists may need to consider quieter sources or rethink the original connection. Then there's the statistical test. Researchers will ask how likely it is that background events could create the observed pattern by chance. This is where an exciting headline has to face the hardest question in science. Could we be wrong? That's not a weakness. It's the system working exactly as intended. A strong scientific claim should survive attempts to destroy it. Researchers then check the data again. They test different assumptions. They compare alternative explanations. Independent teams examine the evidence. Only after the signal keeps surviving those challenges does confidence grow. And if the evidence eventually becomes strong enough, the implications could reach far beyond one pulse. Scientists could learn more about how particles are accelerated near the center of the Milky Way. They could identify hidden cosmic ray engines. They might discover that objects we already know about are capable of producing far more energetic particles than expected. But there's another outcome. The signal could disappear under closer analysis. Maybe the events were unrelated. Maybe the apparent direction was misleading. Maybe background noise created a pattern that looked extraordinary for a short time. Even that result would matter. Science doesn't become weaker when an exciting idea fails. It becomes sharper. Still, if the evidence holds, something remarkable happens. For the first time, researchers could have a particle-based clue pointing toward one of the most extreme environments in our galaxy. And those particles wouldn't just tell us where something happened. They could tell us what kind of physics happened there. That's the real reason this story matters. We're learning to study the universe through messengers that don't shine. A signal invisible to human eyes may still carry a story across 26,000 light years. The only question now is whether the data will confirm that story. If it does, an invisible particle stream could reveal hidden violence at our galaxy's heart. Subscribe for the next update and comment "Signal"